கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல யூடியூப் தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட்
கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல யூடியூப் தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட் அப்புறம் அங்கே எடுத்து கொடுக்க முடியுமா அது வந்து போன
கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட் ஷேர் அப்புறம் அங்கே எடுத்து கொடுக்க முடியுமா அது வந்து போன
கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட் ஷேர் அப்புறம் அங்கே எடுத்து கொடுக்க முடியுமா அது வந்து போன
கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட் ஷேர் அப்புறம் அங்கே எடுத்து கொடுக்க முடியுமா அது வந்து போன
கீழே வைங்க. மேலே MTP கீழே தூக்கி
சரி யூடியூப்ல பாருங்க வெப்சைட்ல தெரியுமா உங்களுக்கு காலேஜ் வெப்சைட் ஷேர் அப்புறம் அங்கே எடுத்து கொடுக்க முடியுமா அது வந்து போன
கீழே வைங்க. மேலே MTP வருவா.
Kamal Kumar sir, shall we start the session?
Yes, sir. You can start, sir.
Yeah, proceed.
Good afternoon to one and all present here. We will now start this section. We welcome our Honorable Chief Guest, Dr. Kamal Kumar sir, and the title of the today's session is Energy of Craft and New Updates. Now I call upon Dr. Gunasekar sir to address the speaker, Dr. Kamal Kumar sir, for this session. Thank you.
Good afternoon to one and all. I, Dr. T. Gunasekar, Associate Professor of Mathematics. I am glad to introduce our research person of this session, Dr. M. Kamal Kumar sir. Currently, he is working as a Professor of Mathematics in Information Technology Department, University of Technology and Applied Science in Oman. He has obtained his degrees from reputed institutions and universities. He has 20 years of academic, research, and administrative experience in various reputed institutions. He published 40 research articles in the reputed international journals like SCI, Above Science, Focus, and UGC CAR journals. Also, he participated in the presented research article in the various national and international conferences. He is a technical committee member and session chair for the various seminars, national and national conferences. Also, he is an editor, reviewer in the various international journals. He is acting as a research person in the various workshops, FDP, and webinars. He is also organized and actively participated in many workshops, webinars, and guest lectures. He was honored by the institution and various agencies for his excellency and contribution in various fields. He has gained more research scholars. We are very grateful to welcome you, sir, on this contribution of this online international faculty development program and current trends in communications of mathematics. Thank you, sir.
Thank you very much, sir. Can I start, sir?
Yeah, now I hand over the section to Kamal Kumar, sir. Please, sir, proceed, sir.
Yes, sir. Thank you very much, sir.
He is also organized and actively participated in many workshops, webinars, and guest lectures. He was honored by the institution and various agencies for his excellency and contribution in various fields. He has gained more research scholars. We are very grateful to welcome you, sir, on this contribution of this
Can you see the screen, sir?
faculty development You are visible, sir. You are.
Thank you very much. Oh, okay, sir. Can
Yes,
I start, sir?
Yes, sir. Yes, sir. Yes, sir. Visible.
Yeah.
Now I hand over the
First, thanks for introducing me, sir. Gunashekar, sir. Thank you very much.
Please, sir, proceed, sir.
And I congratulate the organizers for conducting such wonderful FDP. It's been a great success. And before I start, I want to thank the management, principal, HOD, and all the organizers team for giving me an opportunity. So today my talk is about the energy of graph, and I want to talk about something new happening in this energy of graph. So this will be my outline. First, I am going to talk about introduction, energy of graph, journal of modeling and intelligent computing. It's an Scopus journal. Then we can results and discussions. Okay. So here, first energy of graph. So energy of graph is defined. It was about approximately total pi electron energy of hydrocarbons. It was basically defined on 1930s, and it was Ivan Goodman in 1978. He defined the energy of graph as the sum of the eigenvalues. This is the definition of the graph. If a graph which is having uh, m bodies and n edges, and the sum of the eigenvalues is nothing but defined as the energy of the graph. Now here, so first what we are going to do is take an adjacency matrix. Adjacency matrix where Aij is 1 if Vi is adjacent to Vj. Very common matrix, everybody know about this. Aij is equal to 0. So the sum of the adjacency, suppose you take a carbon atom, any atom, hydrocarbon was first started. So if you take any carbon atom, you take it as, if you take a butadiene, the molecular graph. So this is the compound, this is the molecular graph, and this is the adjacency matrix of the molecular graph. And we can find the eigenvalues using some normal techniques or MATLAB codes or some online calculators. You can find the eigenvalues of this matrix and the sum of the absolute values. This is what we call the energy of this graph. So this is how the Evan Goodman in around 1970s he defined what is called an energy of graphs. Now here, how we are connecting the molecule and the molecular graph and the compound. So here there are this graph terminology and some chemical terminology. Molecular is nothing but structural formula. Vertex is nothing but atom. Edges are bond. Degrees are valencies. So like this, we can define everything that is there in the graph terminology with some components in the chemical terminology. So like characteristic polynomials, nothing but secular determinant, topology of a molecular orbital, energy levels, and different concepts can be interpreted of whatever we are doing in terms of graph. Now this energy of graph is 1930s. It was first started. The idea was started by Coulson integral theorem, which gives an integral formula for finding the energy of the graph by atom electron energy of this graph. So here, for example, if I take this graph, P2, so we can find the characteristic polynomial. Then using the colossal integral theorem, if we evaluate using the integration, we get to root 2 as the energy of the graph. The same thing can be done in a much more easier way. So the matrix, I can take adjacency matrix, find the characteristic polynomial, eigenvalues, and energy of the graph. So this is very interesting to say that that the adjacency, energy that we obtain from the adjacency matrix is the same as the energy obtained from the integral theorem. So this is a, because of this, the energy of the graph was very interesting, and many people have learned about it, and it is very interesting topic because it's much more easier to get the energy of the graphs in a with help of the adjacency matrix. Now, what is the use of studying this? So, energy of the matrix, in what way is going to help us, or is it really worth studying it? Gives an insight about the molecule, then the degree folding, long chain, and all this heat. Basically, when Goodman started the energy of the graph, basically it was said that the energy of the graph is something related to the heat formation of the hydrocarbons. Heat formation of the hydrocarbons related to the total pi electron energy. So it was like some physical application related to this. So there was much interest in this subject. So the heat formation of hydrocarbon is one of the important topic in chemistry, which gives an idea about the stability of the compound, bonding structures, and the connectivity of the atom. So many of the concepts are related with the heat formation of hydrocarbon. So this is what is the main application, if we say, with respect to energy of the graph. So it's based on Huckel molecular orbital theory. So prediction of stability and pi electron systems. So this eigenvalues on not only eigenvalues and eigenvectors. The eigenvalues and eigenvectors gives a insight about the geometry of associated linear transformations. So eigenvalues and eigenvectors, here we are just adding and we are finding the energy of the graph. But literally, the eigenvalues and eigenvectors can be interpreted in an enormous way because the applications of eigenvalues and eigenvectors are enormous. So with respect to compound, we can only talk about eigenvalues and eigenvalues, but we don't much interpret about the eigenvectors. But if you talk about geometry, we can get into much more applications of eigenvalues and eigenvectors. Then there are recent developments in energy of the graph is nothing but there are some applications in biology, medicine, and image processing with respect to eigenvalues and eigenvectors. So from the prior work of Coulson, that is 1930s. Coulson was the first guy who introduced this energy components in 1930s. Then it was Ivan Goodman who introduced in 1970s. So, so from that onwards, there was mathematical properties of pi electron energy was very much calculated with respect to Huckel molecular orbital theory. Now here, if you see in over last 50 years, so around when Ivan Goodman introduced in 1970s, so how did the subject take into shape? So if you see here in the past 50 years, so almost worldwide, many researchers are working on energy of graph. If you see, basically from China and India, there are majority of them are working on this. And there are various papers, thousands of papers are there with respect to energy of the graph. Now here, so Ivan Gutman, who first introduced the energy of the graph concept in 1970, he himself has done a survey. 1917, he done a survey like how the subject has grown. This is the paper, Survey of Energy of Graph. So in the mathematics interested research, he did a survey and found out how the energy of the graphs, the topic itself has grown in such an enormous way. So this is given. If you see this from 1996, if you see in the last 10 to 15 years, there are many researchers working on energy of graphs. And if you see energy of graphs, there are many different types of energy. And in this paper, Evan Putman has recognized some 63 to 70 different types of energies of graph, from Laplacian to pi energy or minimum covering or domination energy. This is what we have introduced. The domination energy is what we have introduced a new types of energy. This is what we are working for from 2 3 years. Then we changed our weight in a different new approach. Okay, let's see that. So these are different types of domination energy. To tell you that domination energy are more than 50 types or 60 types, different types of energies which newly introduced by every mathematicians, and many people are working on it. So in these different types of energy, so first I would like to just discuss a few minutes about the domination energy which we have introduced. Then we'll go for the new approach. Now here, different types of energy. There are around, if you see now when you survey as of now, there are more than 90 different types of energy. Very familiar is Laplacian, skew Laplacian, distance, matching, covering, a lot of types of energy. So domination energy is what we introduced. So this is Professor E. Sampath Kumar. Uh, he was the first person who gave us the idea about the domination energy. So with this guidance, we were able to introduce the domination energy of the graph. So first Sampath Kumar, he was the first person who gave an idea about how to represent the vertex of the graph by means of a matrix. Usually when we talk about adjacency matrix, it's about only the adjacency. So the vertex of the graph are not much significant with respect to matrix. Now, if you see, he was the first person. He said that we can introduce the vertex also in matrix. So, how do we introduce the vertex in a matrix? Suppose you take any subset, any set, S of a vertex, you can represent the set S by form of matrix by replacing the principal diagonal elements. So the principal in adjacency matrix, principal elements will be always 0. So in principal diagram elements Aij, we can replace it as 1 if and only if the vertex I belongs to set. So this concept of introducing the vertex in the matrix, so the matrix thus obtained, we call it as a matrix set of the matrix which is obtained from the set S denoted by S, and the energy we call it as set energy. So the adjacency matrix will replace Aii by 1 if Vi belongs to the vertex belongs to the set. So when then we will get a set energy. So this set can be any possible set. It could be matching, it could be covering. Many types of sets are can be defined with respect to this. So one of the important is a domination. So my core area is domination theory of the graphs. So where we have worked on Roman and inverse Roman domination of graphs. So what we thought was, let us take the set as domination set and let us try to find out the domination energy. So first we'll define what is domination set. This domination is also is one of the vast area. So domination there are more than 100 different types of dominations defined, and there is a large uh, number of papers with respect to domination. So we thought like energy is also is one of the growing topics in mathematics, and domination is also there. If we mix this energy and domination, so you have energy more than 100 types, um, and what we call in energy 100 types and domination 100 types. So you can't get into 100 plus 100. So you get different combinations. So it become a huge topic to survey. So first, a domination is a subset S is said to be a domination set if a vertex not in S is adjacent to at least one vertex in S. So no proper subset of S is said to no proper subset of S is a dominating set if S is said to be a minimal dominating set, because dominating set is not unique. So dominating set can be minimal. So minimal dominating set. The cardinality of the minimal dominating set is called the domination number divided by gamma of domination. Let's just start an example like this. Suppose this is a graph. These are all the subsets, all the possible subsets of the graphs. You can singular, 2, 3, cardinality 3, 4, all the subsets. So we call a set, a subset of this is a dominating set if every vertex not in the set S is adjacent to one of this. For example, if I say B is a dominating set because all the vertex apart from B is adjacent to B. I can say AC also. AC is also dominating set because all the vertex which is not in AC will be adjacent to at least one vertex of this set. So among all this, the cardinality, the minimum cardinality is called the domination number, minimal domination number or domination number. So usually we say domination is nothing but labeling of the vertex by 0 and 1, such that every vertex which is labeled 0 must be adjacent to at least one vertex which is labeled 1. That is what we call domination. If we talk about Roman domination, it becomes labeling of the graphs with vertex 0, 1, 2, such that every vertex labeled 0 is adjacent to at least one vertex labeled 2. So Roman domination was invented by uh, I think Hydrocarbon. So we tried to introduce the inverse Roman domination. So that is our contribution in domination theory. So now we combine the domination energy and Roman domination energy. So I already said the set can be represented with Aij is equal to 1 if the vertex belongs to set. So similarly, if you take the set as domination set, then the energy obtained from that is called the uh, Roman domination energy. Now here, then if we talk about domination, then there is a issue like the domination set is not unique. So you have minimal, we have maximal, we have some same minimal set with minimal domination number with the different sets. So a lot of possibilities are there. So what we defined was, we told okay, if it is just a set. So in a graph, if you have 5 vertex, so let us take starting from 1 to 5. We will find all the energies from 1 to 5. So starting from minimal, so we define not the maximal, we say maximum. Maximum means is nothing but all vertex in the set. That means all principal elements is one. That is what we defined as maximal. So there is difference between maximum domination energy and maximal. Maximal means the maximal dominating set. So we are not talking about maximal dominating set, we are talking about maximum. So all the principal elements will be made one. Alright, okay, let me talk at an example. Suppose I take a domination set of K4. In K4, what happens is the adjacency matrix. So the dominating element is one. The domination number is one. So if you take any vertex, all the vertex are adjacent to this. So the principal diagonal elements will be replaced by one. So for this, we get a characteristic polynomial and we get an eigen values. Because the matrix is symmetry, so you get the eigenvalues can be ordered, rearranged, and the absolute value is nothing but the eigenvalue. Some of the eigenvalues is called the domination energy. So this we say minimal because we have taken it as one. So some people say this one, you why did you take it? Why can't you take it second or third or fourth? So wherever you take using matrix row operation, interchanging two rows and two columns, so you get back the same matrix. So it means to tell that one this one if I put wherever I want, you still get the same. So this is minimal domination energy. So this can be like 1, 2, 3, 1, 2, 3, 4. So from minimal to maximal, we can just check the domination energy of the graph. Okay, just I want to give an example. For example, if I take K2, complete graph, K2 to K3, K8, like this. So this is the minimal domination energy. This is the maximal minimal and maximum. Mean to say that 2 is the minimal domination energy and 2.2 is the maximum energy. We find what is the range. So whatever it means today, when I say the range, it means to tell that you starting from one vertex, putting here and putting the one in the four AII. So all the energy, whatever you talk about, it will be between 2 and 2.2. This is the range. So any energy is range. We can points for set 1, set is equal to 0, 1, 2. We put 0. This when I say set is equal to 0, this is the energy of the graph. The normal energy of the graph that was defined by Evan Gutmann in 1970. So we can take S is equal to 1, becomes domination set. If we take 2 like this, we can just plot it and try to understand how the range or the blue one is actually the energy. We can analyze this individually set energy. We can find when is S is equal to 0, 1, 2, 3. What is the behavior of the energies of the graphs? So this if I take for path. So we can generalize this and we can find the energies of the graph for a path or a cycle or any other graphs, but we cannot generalize it. There are some issues in finding the domination energy of a generalized graph. We can get a bond but not equal to. So these are just we have done some analysis to check the range when S is equal to 1, 2, 3. What is the suppose P8 starting from S is equal to 1 to 8. So 9.8 to 10.8. So this kind of analysis can be done to understand what is the relation between energy and minimal and maximal, how they are differentiating with each other. So we tried with few graphs to just tell you like the set energy or the domination energy is of this kind. So for cycles we can try and we can find domination energy for all the graphs. This is for the stars. So this is the energy of the graph. This is the minimal energy. This is the maximum energy. When I say maximum energy, it means in the principal elements, I put all the principal elements as one. So 11.3. So if I say the range, it will be 5.9. That means any energy from 1 to 0 to 0 to the maximum set, maximum 8, you will get the energy within this range. Now, once we define the domination energy, so once we define the domination energy, then what we try to do is nothing but we try to analyze the analog. So what was the results that was obtained in energy of the graph? The same kind of analog results for the domination energy. Now here, if we see for not a complete graph, not a complete graph, the energy of the graphs will be between minimum and maximum. Domination energy, this is the domination energy between minimum and maximum. There are some error factors which is less than one. If it is not a complete graph, it is not a complete graph, energy of the graph will be always less than the domination energy. Energy of the graph will be always less than the domination. If it is a complete graph, the energy of the graph will be always more than the domination energy. The energy of the graph will be always more than. So this kind of analogs or this kind of similar results that we try to obtain for the energy of the graph. Now here for P2 and C6, we found that the spectra is different, but the energy is the same. That means if I take P2, if I take P2, then I can have yeah, P1 and P1. There are two vertex, first vertex and second vertex. First vertex and second vertex, maybe the spectra is same, but the energy is sorry, spectra may be different, energy is the same. With respect to symmetry of the graphs, symmetry of the set, the energy also will be same. For example, uh, if I take a cycle of six vertex, so the domination energy is 2. So we can do any two you take, maybe 1 and 5 or 2 and 4. The spectra will be different, but the energy of the graph will be same. And this analog, energy of the sum, the eigenvalue square, the sum of all the eigenvalue square will be 2 times the number of edges. This is the energy of the graph in equality. So we have for set energy what will be there. So for the domination energy or any set energy when you put it, so the sum of the squares of the eigenvalue will be 2m plus the set. Set is nothing but the coordinate of the set which you have taken for calculating the set energy. Now the other part was symmetry. It will be symmetry in nature, and that's what we were trying to do is nothing but most of the time when we try to introduce some new concepts in energy, we try to get the analog of the previous. So whatever they have done in the eigen energy of the graph, so lambda ij is equal to minus m. So what will happen to domination energy? It will be greater than or equal to minus m. It will not be equal, it will be greater than minus 1, and strictly greater than minus m when set energy is not equal to 1. In eigenvalues of the energy, if I add, it will get 0. But in domination energy or the set energy in general, if I add, the sum of the eigenvalues will not be 0, it will be the cardinality of the set. In eigenvalue, the lambda will be equal to square root of the maximum degree. Here it will be square root plus 1. So this kind of analog we have done. And characteristic polynomial. In eigenvalue, the characteristic polynomial, when you are getting what is the relation between the coefficient of uh, a polynomial is a1 a2, that is in energy it will be a1 will be 0, minus a2 will be the number of edges, minus a3 will be the twice the number of triangles in a graph. So this analog, what will happen the same with respect to domination energy. So that we have done this is what the research we have been doing for some time, and we have published many papers with respect to domination energy. You can just Google and find it. In domination energy, what will happen? A1 and A2 are same for all characteristic polynomials with the same cardinality of the set. So because I told that here in domination set you will have from S1 to 2, 3, 4, everything up to AI to be complete one. A1 and A2 will be the same. A1 will be minus S, cardinality of the set. A2 will be with respect to the cardinal, that is if scalarity is 1, A2 will be minus E. That is the edges as it is. Number of edges in the graph. If the scalarity of set is 2, A2 will be U1 plus E. That is edges plus 1. So like this we have found the analog of what happened to the coefficients with respect to the characteristic polynomial if we are dealing with an set energy or the domination energy. Now here, then bounds. Usually this is what we do. Once we get into this, we start about bounds. When if the graph is not equal to a complete graph, n is greater than 3, then we get the domination energy, the minimal domination energy. So mainly we focus not on the maximal domination energy, maximum. We focus on the minimum domination. That means this, when I write like this gamma minimum, it means that the domination energy obtained for the minimal domination set. That means for the domination number. For the domination number, the minimum domination number, the energy is obtained, so we get this one. This is cardinality of set. This is what we call determinant of A. The same, like if it is not equal to Kn, get some bond like domination energy is greater than or equal to 2 square root of n plus lambda. Now, if it is equal to complete graph, usually we talk about basically the standard graphs are when we do anything, we try to do with complete graph or a star or a cycle or a path. These are a wheel. These are the general graphs. We try to get the results so that we can try and compare with the energy of the graphs. Now here, this was the result obtained Malikar, Hampioli and all this for the energy of the graph. Energy of is less than uh, 2m, some bond which was obtained for the energy of the graph. So we try to find what is the similarity. This is for the R regular graph. R regular graph, this is the energy, the result obtained by them. So we try to compare and find out what happens to this or this results with respect to energy of graph. This is what usually we try to do it. So minimum energy is nothing but 2m plus uh, cardinality of set S with this. So for a K regular graph, so we get some kind of bonds here. Now what we do after that, what we do, we try to characterize. If domination number is 1, what will be the domination energy? So if domination number is 1, then what kind of graphs you get? So domination energy is 1 means maybe you get a complete graph or a star. So we can find the absolute what we call domination, minimal domination energy of the graphs using normal techniques. Generalization you can do, mathematical induction you can do, or you can just do by solving the characteristic polynomial and we get an n cross n matrix. Uh, there are some techniques to find the eigenvalues manually and then adding you can get the results. So I'm not showing the results there. So this is what we call the domination energy. We get the domination energy for star and similarly for n is equal to 2. So n is equal to 2 we get for Thorn rod. So this kind of what is Thorn rod is nothing but you have two stars and connected by a path. So for n is for domination number 2 P2, if there are a path with path n get 2 and 3 or 4. So this is what is thorn rod P2T. P2T means it means you have the path with two vertex and you have a star with T minus 1 uh, edges or what you call isolated vertex with degree 1. So we found this as 2 and 3. If it is 3, then we go for Thorny stars and Thorny rings. These are some kind of chemical. This was introduced by an US mathematician, which when he was dealing with some chemical objects. So this is Thorny stars and Thorny rings. Thorny stars are nothing but you have a star and all the pendant vertex is having a star. This is what we call a Thorn star and Thorn rings. Thorn rings is nothing but you have a cycle with the pendant vertex, or you can have a star or a structure of a star like this. So we can find if domination number is 3, domination number is 4. You get this kind. This is the kind of structures when you get domination number is 3 or 4. So for this kind of structures, what will be the domination energy of the graph? So domination energy like this equal to, we cannot find for all graphs. Even for a wheel, we cannot find the equal to sign. We'll get an inequality less than or greater than. So finding the characteristic polynomial. This remember when we are trying to do this, it is for an n cross n matrix. We are finding the characteristic polynomial and eigenvalues for an n cross n matrix, and summing them and getting the eigenvalues. So it's not possible for all graphs, but few graphs we can get equal to bonds, and majority we can get less than or equal to. Even for 4. Even for 4, we can get like this. Now, when we did all this research, what happens to this is nothing but when it started, we say that the energy of the graph is used for finding the what we call specific heat of some hydrocarbon. But when we are dealing like this, we get into theoretical chemistry. Theoretical chemistry means we are doing only theory, but it has no physical application. So whenever we try to present this kind of domination energy papers in some chemical conferences, some chemistry conferences, because we are looking for this application. So usually there are a lot of limitations in this. So there are some problems when defining the energy of the graph. So this is what we are talking about the new approach here. Whenever we go there, the various types of bond, the various types, single bond, double bond, triple bond, cannot be represented in our matrix, adjacency matrix, because we're taking a single edge. So when we compare the molecular graph to the chemical component, the bond concept is vanished because we are taking a only adjacency. One atom is adjacent another atom, draw a single edge. What about the double bond, triple bond, or other bond? This cannot be represented in term. So here there are some limitations in energy of the graph. Then what about the different atoms? So when we convert the molecular graph to energy of the graphs, the atoms are just point, whether it is carbon or oxygen or nitrogen, it doesn't matter to us because we are just taking a dot. So these are the limitations. Different atoms cannot be represented in the adjacency matrix. Oh, and various types of atoms are there. So how could this lead to the application part? So these are some limitations. Then what about the hydrogen atoms? When we convert the chemical components to the, first it first started with hydrocarbons. Of course, we can do for all carbons, all atoms, even when all atoms are there. Hydrogen atoms are not considered for calculation. So why the hydrogen atoms are not calculated for the control project? Whether the hydrogen atoms have no significance with respect to an molecule, or when we see the literature, it was in 1930s or 70s due to the lack of computations. Usually, people avoided the hydrogen atoms to limit the calculation. That is what we tried to. In some literary literature, it is given that the hydrogen atoms was ignored from the calculations of energy because the computation is more. But now we don't have a issue because we can compute 100 or even 200 plus 200 matrix also we can compute. It's a very easier way, much more easier way. You can easily compute even 100 plus 100 matrix within second and get the eigen values or eigen vector, whatever it is. So why should we restrict the hydrogen atoms? So these are the limitations. So the significance of double bond, triple bond atoms cannot be interpreted, and to overcome this limitation. Now, is there a matrix? Now we need to check in our literature, is there a matrix where these limitations can be overcome? So we try to introduce the atom connectivity matrix and connectivity matrix. This matrix is not, we have not introduced, it is already there in some literature used for a specific reason. So we try to take that matrix and try to find the energy of the graph. So this is a new approach because we are trying to overcome the limitation that is there in the energy of the graphs, and all the limitations like hydrogen or the atoms or the bonds can be introduced with the help of a matrix, and we can try to study in a better way. Now here, so there's other limitations also. Now here, already I told like molecular bond, hydrogen atoms. This is already the what we call the energy of the graph is all connected to Huckel molecular orbital theory. So that is why we say most of the time the energy of the comes in theoretical chemistry. There is no practical applications for it. So what we do is nothing but we find energy of the star or a complete graph or a path or R regular graph, whatever we say that. So we think like, do we have any graphs of this kind? Do we have any compound of this kind so that the physical representation can be implemented? Most of the time there is no compound connected to the can I hear? Is it? I'm audible, sir. Is it fine?
Yes, sir,
Yes,
you
sir.
are audible.
Okay. Okay.
Yes, sir.
Okay. So what happens is nothing but the Huckel molecular orbital theory itself is very old, 1930s.
Yes,
But
sir.
after 1930s, there are many other complex orbital theory has been defined. So when we do some what you call synthesis of new molecules or something like that, where millions of dollars have been put on, we don't try to do with the theoretical chemistry. So the molecular orbital theory itself is little old to in terms of understanding. So that is why we just say that whatever energy of graphs you're finding is limited to theoretical chemistry. It's of not much use in practical. That is the kind of analysis comes. So, so what we do is nothing but this connectivity and atom connectivity. This is the two kinds of matrix we try to introduce that, so that this will come the overcome the limitations in the previous energy of the this is the idea what we are talking about, the new approach. First we are also doing like others, like where we are doing the energy of the graphs with all kinds of graphs available in the math. So we can just find energy and get it, but when we of course we can get a lot of papers, but when we go to some chemistry or some other concept, usually the some applications is lagging there. So here what we do is nothing but in this case, so where did this atom connectivity and connectivity matrix come from? So if you see that most of the atoms can be represented in the form of a computer. So suppose we are not drawing a suppose if you have a think of if you have a database of some molecules, then how the molecules have stored in the computer. So, but when we see in the literary survey, there is no unique way of saving the information of molecules in computer. That means till now there is no unique way to save the molecular informations in a computer. So one of the ways is nothing but atom connectivity and connectivity matrix. So these two matrix were usually introduced by uh, Spider. Because why means to represent the computer representation of the molecules. Because usually what we do is nothing but most of the time now because of the computation power, uh, uh, molecule information is represented in the form of a computer. So this computer can check the two similarity of the atoms or molecules. Many possibilities are there. So the computer representation was the original reason for introducing atom connectivity and connectivity matrix. So what happens is nothing but see, when you want to store the molecule in a computer, then all the information is required: atoms, bonds, or maybe some other things. So all the things we need to store in the computer. So we take that matrix and try to find the energy of the graphs. Then we saw in literature anybody have worked on this. Not no, one or two people have worked, but it's not very significant. So oh, we take this matrix and try to work the energy of the graph. So atom connectivity matrix. So it was first proposed by Spider in. You can see the. I'll show you the reference at the end. For you, basically he used these two matrix to represent the computer-oriented chemical nomenclature. That means to say that the matrix representation was just an information to store the molecular information in the computer. So here we take Bij. So Bij is nothing but the vertex Ij are adjacent, where Bij is nothing but the bond order. Si stands for the chemical symbol of the atom. So the Bij, where you can use Sij to be 0 or the bond value to be 1, 1.52 or 3. If it is a singular bond, 1 aromatic, double bond, triple bond. For triple bond you can use 3, for double bond you can 2, for aromatic bonds you can use 1.5, and you can the numbers can be changed with respect to the bond. So we can get the bond. And so from this matrix what happened is nothing but the bond, single bond, double bond, triple bond can be introduced in the matrix. So what happens that one limitation, some people say the bond you're taking single bond, there is no representation of double bond, triple bond is we can overcome the limitation with this matrix. And some other people say that okay, what about atom? If it is a carbon atom, hydrogen atom, or an oxygen or nitrogen, how are you going to represent that in terms of the matrix? Now here in energy of the graphs, all atoms will become like a node, and there is no significance about the carbon atom or hydrogen atom or oxygen nitrogen, whatever is there, all are points. But here what happens in connectivity matrix, we can represent the Si, that is The Ni is nothing but the atomic number of the molecule. So whatever number you are taking, if you somebody say, okay, why you take atomic number? Why do you take atomic mass or some other quantity which represents the atom? This we are taking this because it's already in the literature by Spider. Uh, Around 1964 or 60s, late 60s, molecular structure. So in this case, there is two concepts. One is hydrogen with hydrogen and without hydrogen. So let me give an example for it. So it will be easy. So again, what happens? So we have worked on some standard graph because I told you there are maybe 100 types of energy. We take the familiar energy and try to work on it. So we have worked on energy, distance. These are the familiar one. Laplace and Laplacian. So we define Laplace energy. You know that from the Laplace matrix. So Laplace matrix is nothing but the what you call the degree matrix. The principal elements is nothing but the degree of the atoms minus adjacency matrix D minus E. So the energy that obtained we call it as energy because in literature if you see Laplace energy and Laplacian energy. So Laplace energy was introduced by Evan Goodwin. Laplace energy is what we are talking. Uh, D minus A, that is the degree matrix minus adjacency matrix. You get the Laplace matrix. With that, you find the energy. We call it as Laplace energy. So this was defined by as Laplace energy. That's all. Laplace energy defined by Ivan Goodman is nothing but the eigen values are subtracted by 2m by m. 2 number of edges divided by number of vertices. So this is d minus a will give you Laplace, d plus a will give you sine plus Laplace. So these are some basic, very familiar types of energy, and same thing put it a domination. So domination energy, what we introduce, so we try to see the energy and domination energy how it works. So these are the types of graphs we are trying to what we call analyze. So here what happens is nothing but so our idea of generalized graph finding the bonds or what we call bonds, inequalities. So we stop that and we get to try to find some applications for it. For example, if you take this C2H2 ethane. So this is the molecular structure of the bond with hydrogen, without hydrogen. Usually when we take the energy of the graph, we ignore the hydrogen. So if you ignore the hydrogen, you get like this. Now if you see this is adjacency matrix. In adjacency matrix, what happens is nothing but the triple bond from 1 to 2. You have a triple bond. It is not here. You represent only the adjacency. 1 to 2 is 1. So with this energy, we try to find the graph. One minute. Okay. Now here, uh, with this matrix, this is a normal adjacency matrix. You find the energy. This is what we call energy of the graph. So how this matrix and come to atom connectivity matrix. In atom connectivity matrix, what happens is nothing but 1 to 2 is represented by the triple bond. So you get a triple bond here. So the bond information of the compound can be put in terms of a matrix. So this is what we call atom connectivity matrix. So if it is a double bond, triple bond, aromatic, so you can put even 1.5 or 1 or 2 or 3 based on the bond structure. Now in this, if you see, there is no information about hydrogen or atom. Here in adjacency, nothing about hydrogen or atom. So no significance here. Here also in atom connectivity, of course you get a bond, but there is no significance of hydrogen or an atom. So what we do is nothing but the hydrogen atoms or the carbon atom can be represented by their atomic number. For example, like this CCHH. So C is the carbon atom, general CC. So 6 is the atomic number. So you can represent hydrogen atomic number is 1. You can represent like this. So I'm telling you again that this why you represent the atomic number because we have taken an atom representation or matrix representation from the literature. So if you somebody says okay, why not take atomic mass or why not take some other physical representation of a compound and represent here? It's up to you. But our goal is uh, to find some physical application with respect to the compound. So can we find the we are finding the energy of the graphs of this component, and we are trying to relate this our research, which is a funded research in our institute. So Oman Research Organization have funded us to do this, and we are doing some research based on this. So here we are representing the carbon atom. So this bond will give a complete information on bond as well as the atom. So this is with hydrogen, without hydrogen, because usually energy of the graph they do without hydrogen. So we thought, okay, well, let us do hydrogen suppressed matrix, non-hydrogen suppressed matrix. That is what is the name given in the literature. So this is how we try to uh, jump from the normal energy of the graphs to the a new idea of this using carbon atom and kinetic matrix. So here what happens, we don't get an arbitrary graph. So now we don't try to find an arbitrary graph or a R regular graph or a cycle or a path or a wheel or something like that. We take a specific compound, try to understand the numbers associated to this compound, and we try to find the application. That means do our calculations resulting in a number, is it useful to find some properties with respect to the compound. So when we take a compound, of course we have hydrocarbons, we have other kinds of compounds. So we are still in a preliminary state to find out the applications of the using distance matrix. So domination. So what we do is nothing but how to introduce the domination matrix here. Here the domination is 2. So you can put adjacency matrix. What happens is adjacency matrix. You can put here 1 and 1. This is the domination matrix. So the domination energy is very interesting because I am just taking a simple domination matrix. If I take Roman domination, it will become 2 1 1. If I take an connected domination, independent domination, or pairwise domination, there are 100 types of domination. If you take maybe inverse domination, maybe there is something else. So you can just try that, and you can the results you can get very large result on this. So here in domination, what happens? 1 and 1, so I can put here 1 and 1. So here also I can put 1 and 1. Here how do I put? Already the principal diagonal elements is already occupied. So how do I do it? So there are many ways to do it. So we have defined it as, we can do it like AI is Ni plus 1. So domination set 1 and the atomic number. So we can do in this way, we have introduced, and we are trying to work on the uh, atom connectivity. So this we call it as connectivity energy and atom connectivity energy. So this is how we define the distance matrix. Now this calculations for hydrogen or non-hydrogen, we can find the characteristic polynomial. Same way you can do it. If you remove the hydrogen, you get only the skeleton of the atom. If you do with hydrogen, you get the complete compound structures. And you can find the characteristic polynomial with MATLAB codes, or as simple as manual calculation may be difficult, because when the number of molecules becomes more, maybe 20, 30, 40, manual calculation doesn't work. MATLAB code is good. If MATLAB code is not good, then you can try with in Google. You can just type matrix calculator. You will get many calculators up to 50 cross 50 or 80 cross 80. They can, you type the matrix, they can get everything to you. Uh, so adjacency matrix, we have calculated the characteristic polynomial for adjacency matrix, atom connectivity matrix, and connectivity matrix. So the energy that obtained is, this is the normal energy. This is atom connectivity energy. This is connectivity energy. So this is how we try to define the energies of the graph. Now here atom connectivity matrix. So this we try to uh, get the energy of the graph. We have found the different types of energy of graphs, and we try to analyze what is the relation between them. Of course, this relations you can do it like, what is the relation between them? It is 2, 6, it's increasing, decreasing. This can be done, but our main goal is, will these numbers or help us to find some physical uh, properties of the matrix. In generally to say that uh, taking a compound, doing analysis in the lab, getting a result, some properties can we do without that. So this is our main goal, and this is our research continuing in this part. Now here, same thing, domination energy. So This is the energies obtained from adjacency matrix. This is normal energy. This we call atom conductivity energy, and this we call conductivity energy. So these two energies that is different from this, because in this I told you, like in this atoms bonds has no significant. In this atom conductivity, bond significance is there, only bonds, but conductivity matrix, it has a significance of bonds as well as the atoms. So we say that this is a better interpretation of a molecule when compared to energy. So this is the things we got, and this is just I want to show you the table, like the calculations and the numbers we have got energy. So suppose I take ethane C2H2. So of course I have taken some 10 or 15 different types of energy. Not even 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 plus 9 normal 9 types of energy which is familiarly used, and with this 9 we get another 9 with the domination, introducing the domination energy. So we try to find these numbers. So of course the initial results, like we have analyzed whether where it is increasing, where it is decreasing, what is the range, how the characteristic polynomials are varying. So this kind of analysis can be done like we did before. But our main goal is whether these numbers can be related to some physical properties of this molecule, and how it will be differentiated from hydrocarbons and non-hydrocarbons. So as of now, we are focused on hydrocarbons because hydrocarbons are more easier way to understand and easy way to calculation than the other kinds of atom. So in this hydrocarbons, now we are trying to analyze. So that is why I don't want to do that. What is the bonds you get? Because here in this type of graph, you don't get any bonds. You don't get any what you call generalized form, because there is only one atom. If you say for a cycle, then you will say C3, C4, C5, and you say Cn. For Cn, you this is the energy, or for P1, P2, and Pn, this is the energy, and a generalized matrix for a graph G. You can talk about bonds, but when we get into this atom kinetic matrix and kinetic matrix, there is no generalization. It's about a compound. For a compound, what is the energy? For a different compound, so you talk about only the different types of compounds. So you get different types of different kinds of components are there. How is your energy with this molecule to that molecule? So how you can compare the energy with the molecule to molecule, and we are working on the physical representation. Our main goal is on the physical representation. How can I use these numbers to find the physical component of this uh, component in chemistry? So the only advantage from moving to energy to uh, what you call atom kinetic energy or kinetic energy is nothing but the limitations which is already existing in the energy of the graph can be overcome with this new two types of matrix. So there are many open problems in this uh, to study the atom connectivity and connectivity matrix of other components. We can study about other components, and we are working. The many components are there. Uh, Huge components are there, and we are finding how this is related from one to another. For example, if I take hydrocarbon, I get energy of this. If I try to relate this with some property, will the same property be obtained for a component which is not a hydrocarbon? So this kind of analysis we are trying to do. We are trying to get some database and checking whether our results will be used in some physical representation. The significance of this energy with respect to the physical properties. Our main goal is to get the physical properties, because the energy what we get is nothing but becomes like theoretical chemistry. We want to try some physical applications with this new kind of matrix. Of course, we can compare the energy, atom kinetic energy, and different types of energies are there. So we can find the relation between the structure. So this is our main thing, how the structure of the component, structure of the compound and the energy of the compound is connected. So this kind of relations we are trying to find using our research. So these are the references we have done. So this is the first paper. Many people when they are doing in the literature, when we see of course there is some people say that the domination energy and the minimal covering energy are both same. So if you see that the covering energy was first started by Sampath Kumar. This is the first paper uh, in the Proceedings of National Workshop on Graph Theory. This is the first paper where Sampath Kumar introduced 2010 introduced the concept of representing a set in terms of a matrix. And this was the paper, atom connectivity matrix and stochastic polynomial, new computer orientation chemical nomenclature. It's around 2012 and 13. Around 2012 and 13, this was the paper. In 1964, there is another paper, 1964, where Spread introduced the atom connectivity matrix to represent in terms of matrix, in terms of molecule representation, computer representation. So when we talk about computer representation, a lot of analysis is done when you represent a molecule in terms of a computer. So we are taking the same matrix which we have used there to find the energy of the graphs. So I thank for your patience listening. I think we have more time for discussion. So if you have any questions, you can ask me. So I thank for your patience listening. I think we have more time for discussion. So this was funded. This is funding by this. We are got a funding for this. This is funded by our research council, Sultanata Poman. They have funded this project, and we are working on this. So if you have any suggestions, any doubt, you can ask me. So I've completed a little bit before in time, so that any queries or any other suggestions can be discussed. So I've completed a little bit before in time, so that anybody have any doubt, any clarification, anything, you
So
can
I have a
open to
question.
question.
So I have a question.
Yes.
Can I ask a question, sir?
Yes.
So instead of adding the eigenvalues to get the energy, sir, can we not
Yeah.
get the eigenvalue for each matrix? Because adding will complicate and interpretations are not possible with that. Separate
Yes, madam.
this eigenvalue of each matrix, if we study, then interpretation can be easier, sir.
Yes, madam. Yes. Actually, what happens is nothing but that is what I told. Our main goal is like why we are adding. That is to find the physical properties. So the research is open. We can add matrix. We can do anything. At the end of the day, is nothing but whether our numbers, what we are getting is it used in any physical way, or we are just getting the some relations or some numbers. That is our main goal. So now when we introduce this matrix, it is open to all, like you can add or subtract, or the domination energy you can put, or anything. At the end of the day, is there any applications for it? So that's the question, madam.
So, but so eigenvalue itself is a very important number. It will have a lot of significance in genetics and proteomics.
Yes, madam. Yes, that's what I told. Eigen energy. When we see that what in energy, if you see, we are just adding it for getting the energy of the graph. It was given in the literature by Evan Goodman. That is why we are talking about energy. But
Okay.
nobody has analyzed. Like for example, if we see that in the literature, if you see, the eigen values are used for what we call. Suppose you what you call if you model a theater, the acoustics can be analyzed with eigenvalues. The car that we are designing with a car, now many people in car designing the acoustics, the speakers, they are doing some analysis in eigenvalues to get the picture. And I have seen some papers where they find the oil inside the earth can be done using the eigenvalues. But what happened is nothing but they are getting the eigenvalues from a very complex structure. We are getting eigenvalues from the molecule. So from where we are getting the eigenvalues, that represent the eigenvalue significance.
Okay. Thank you, sir. Thank
Thank
you,
you.
sir.
So from where we are getting the eigenvalues, that represent the
Thank you, sir.
significance. Thank you, madam. Anything else, madam? Anybody have any doubt?
Thank you, sir. Thank you, sir.
Thank you, sir.
Okay, sir, we conclude now. Tha- Thank you for your remarkable presentation. It is curious to know how to apply our graph theory in different ways. Once again, thank you, sir. Also, I thank all the participants for your cooperation. Now, this session is over. I ask everyone to join the next session at 10:45 a.m. tomorrow. Thank you, sir.
Thank you, ma'am. Thank you, one and all, for your opportunity. Thank you.
Now, this session is over. I ask everyone to join the next session at 10:45 a.m. Thank you, sir.
Madam, kindly send the feedback link. Due to poor network, we got disconnected. Madam, kindly send the feedback link. Due to poor network, we got
The feedback
disconnected.
link is working, sir. The feedback link is working, sir.